Hello, and welcome to Chapter 8. Here we're going to... Hello, and welcome to Chapter 8. This is an introduction to hypothesis testing. So in this short video, we are going to understand the logic of hypothesis testing. We're going to learn how to state hypotheses and locate the critical region, and we're going to conduct a two-tailed z-test and make a decision. So before you start this video, you should have downloaded the handout that says teacher and student-led examples, and the next couple of videos will work through these examples together. So what we're going to be doing now till the end of the semester is called hypothesis testing. And hypothesis testing is a statistical method that uses sample data to evaluate the validity of a hypothesis about a population. So that's one of the reasons we moved from doing z-tests about a single score to doing scores for sample data, because that's what we're going to be using from now on. And we're going to compare that sample data to a population. So basic experimental design is here we have a known population before the treatment. And we're going to take, we know that the mean is, say, 16 here, the standard deviation is 3, and we're going to pull a sample from that. It's going to undergo some sort of treatment, and then we have an unknown population after the treatment. How would that treatment affect that population? So the standard deviation we assume is still going to be about the same, that it's going to universally have the same effect on everybody, so we'd still have that same variance. However, we don't know necessarily what that new mean is. So when we're doing hypothesis tests, we make the assumption that our unknown population mean is the same as our known population mean and that there is no difference between the two. We test to see whether there is a significant difference. So we'll start off by going through a teacher-led example. So again, hopefully you have the handouts downloaded and printed out, and you can follow along as we go through it. So we're going to see over and over again for the rest of the semester these 4 steps that we will do in hypothesis testing. The first one is going to be to state the hypothesis, and we'll come back and go through each of these in detail, but the idea is that when you're stating the hypothesis, you're predicting the expected characteristics of the sample based on that hypothesis. We then need to set our criteria for the decision. We obtain a random sample from the population, we collect data, and we compute the sample statistics, and then finally we make a decision. We compare our obtained sample data with the prediction made from the hypothesis. If consistent, hypothesis is reasonable and we fail to reject. So if our new sample data after the treatment is similar to the population information that we have, we fail to reject it. If it's discrepant, if it's different, the hypothesis is rejected. So now we're going to go into an example. So here the example says a training program designed to have an effect on friendliness is tried on one individual randomly selected from the general public. Among the general public who do not get this training program, the mean on friendliness, let's try that again. And now for an example. A training program designed to have an effect on friendliness is tried in one individual randomly selected from the general public. So we're going to have an N of 1. We're going to call the sample. Their sample size is 1, just for ease of the calculations. Among the general public, so this is people who do not get the training program, the mean on friendliness measure is 30, with a standard deviation of 4. The researchers want to test their hypothesis at the 5% significance level. After going through the training program, this individual takes a friendliness score and gets a score of 40. What should the researchers conclude? So again, here I've just highlighted that for our example here, we're assuming that our N equals 1, and it's a sample, not an individual score. So the information that we have here is that the mean on the friendliness score is 30. So this is general public, so our population mean equals 30. Our significance level is 5%. And the person, the sample person who gets a score of 40. So we're going to say that that's their sample mean equals 40, even though we have an n of 1. The first thing we need to do is state the hypothesis. So we're going to have a null hypothesis. The null hypothesis states that the treatment has no effect. In other words, there's no change, there's no difference, or relationship. The independent variable has no effect on the dependent variable. That treatment had no effect. So in this example, that the training program designed to have an effect on friendliness had no effect. So we're going to write that as H sub O, that's the null hypothesis. This is the mean for our treatment group equals the mean for our population. The alternative hypothesis states that there is a change, there is a difference, or some sort of relationship in the general population. That we're going to note that as H sub 1 says that the mean of the treatment group is different than the mean of the population. So now we want to state the hypotheses for our example here. So we said that for our null hypothesis, or H sub O, we said that our population mean was 30. So now, what does that mean for our null hypothesis? So our null hypothesis, so we've highlighted here the important information that the mean on the friendliness measure is 30. So our population mean equals 30. That means that our null hypothesis, our H sub O, or the population mean of the group that undergoes training, would be the same as our population mean, which would equal to 30. And if we stated it in words, we would say that the training has no effect on friendliness. The treatment, which is our training, has no effect on friendliness, our dependent variable. The alternative hypothesis says that there is a difference, that that training program is going to have an effect. So H sub 1, which is our alternative hypothesis, says that the mean of the group that underwent training, so mu sub training, is not equal to the population mean. So again, that 30 was that population mean. If we state that in words, it says the training, so our treatment here, the training has an effect on friendliness and will cause a change in the mean score. So next we need to set the decision criterion. And so this has to do with that 5% significance level. Okay. So the distribution of sample outcomes is going to be divided. So we're going to have outcomes that are close to the null hypothesis and outcomes that are very different than the null hypothesis. And that's what this diagram here is showing you. So here you have your normal distribution. So here you have your normal distribution, right? And you see we have a line drawn here. And it's kind of arbitrary. This is what the line drawn here has to do with that significance level. And so we have the mean here, and we have these sample means that are close to the null hypothesis. This is the population mean, and we say our null hypothesis is that new distribution of sample means is going to be close to that original sample mean. And then we have these extreme scores here out in the tails. And they're extreme low probability values that the null hypothesis is true. So we have values close to the null hypothesis and very different from the null hypothesis. that into words, a probability value is used to define very unlikely outcomes. So these areas out here in the tail are very unlikely. Another way of thinking about them is that they're boundaries of the critical region, that it's determined by the alpha level. So these boundaries are determined by the alpha level, and these areas out here are critical region. We said 5%, so that gives us an alpha of 0.05. We take that 5%, we divide it by 100. Another common alpha level is 1% or 0.01, and another one is 0.001. So this is just showing you, again, that diagram. We're going to have some very specifics. When we talk about a 5% alpha level, we're talking about a two-tailed test. So here we have one tail and we have two tails. Our boundary, our critical z-score is going to be 1.96, positive and negative. The question is, where did I get 1.96 from an alpha of 0.05? Here's that z-score. If I go over here, the proportion in the tail is 0.025. It's not 0.05. How did I get that? Well, look here, and remember, you have two tails. So you have to take that 0.05, or that 5%, and you have to break it into 2. So 5 divided by 2 is going to give me 2.5, which means I have 2.5% in this tail and 2.5% in that tail. So the proportion in each tail gives me a z-score of 1.96. So the boundary here for an alpha of 0.05 in a two-tailed test is 1.96. To bring it all back together, we look here and we see we've already talked about the extreme scores, this 2.5% at each tail, and that this middle portion is middle 95%. They're high probability values if the null hypothesis is true.